This is section 1.3, consistent systems with infinitely many solutions. If you remember in the previous sections, we would always get a numerical value for each variable, like we'd get x1 is equal to 1, and x2 is equal to 2, and x3 is equal to 3. That would be a unique solution. That was if we were doing Gauss-Jordan elimination and we got that. In this case, we're going to look at some systems where we actually get infinitely many solutions, so there are infinitely many intersection points. Let's check out this section. Section 1.3, consistent systems with infinitely many solutions. Now remember, we say something's consistent if there's at least one solution. Okay, so we're going to be looking specifically at the systems that have infinitely many solutions. All right, now if we were to have two lines, now remember we're dealing with linear equations. That was our very first section, was what is a linear equation? If we're dealing with two lines, what are the three things that could happen? Well, you could have one intersection point because they could cross one time. You could also possibly have no intersection. That would happen if you had two parallel lines. Okay, remember parallel lines never touch each other. So there would be no intersection, there would be no points in common, so there would be no solution to that system. The other thing that could happen with two lines would be you could have infinitely many points. And that would be if you had one line that's just right over top of the other, coinciding lines. Okay, now those are the only three things that can happen. There's no way that I can get two solutions because these are straight lines. They're not going to cross, if they cross at all, they're not going to cross more than once. Okay, so I either have one solution, no solution, or infinitely many solutions. It's the only things that can happen with two lines. The same three possibilities occur with 3x3 systems. Now 3x3 systems are either going to be lines or planes. Let's look specifically at what would happen if we had three planes. There's either going to be one solution, no solution, or infinitely many solutions. And let me see if I can prove that to you. Okay, again, thinking that we have three planes. If that's your first plane, that's your second, and that's your third, as you see, the three of them come together in one point. That has one solution. You can think of it like a corner of a room. Okay, that's three planes coming together in one point. That would be where you'd have one solution. Okay, now again, with three planes, we could have this possibility. What if we had one plane? There's the second, there's the third. As you see, those would be parallel planes. They do not intersect at all. They don't have any points in common, so there's no solution to that system. Okay, another possible thing that could happen. We could have one plane, then look how the second plane just goes right over top of the first. The third goes right over top of the other two. So in this case, I would have infinitely many solutions because all three planes coincide. So far you've seen we had one solution, or we could have no solution, or we could have infinitely many solutions. There's another way that you can get infinitely many solutions with three planes as well. Besides having the three coincide, you could have an intersection. As you see, the three planes intersect in a line. Okay, now a line has infinitely many points on it, and so this again would have infinitely many solutions. So there's a couple different ways we can get infinitely many solutions with three planes. Okay, but still the only things that could happen were one solution, no solution, or infinitely many solutions. There's no way with three planes to get two solutions or five solutions or something crazy like that. We're only going to get either one, none, or infinite. And as we said, this section is mostly going to look at what happens when you have that infinitely many solutions situation. Okay, so let's look at this 2x2 system. It's called 2x2 because we have two variables and two equations. It's x1 plus 2x2 is equal to 3. 2x1 plus 4x2 is equal to 6. If we use Gauss-Jordan elimination to solve that system, remember the first thing we do is put it into an augmented matrix. So let me do that. On the left side, as you see, I have the coefficients, 1 and 2, and then 2 and 4. Those are also coefficients in the second equation. Now I want to eliminate the 2 that's in the second row. I have a 1 already in the upper left-hand corner, the 1, 1 position, but I need for that 2 to become a 0. And the best way to do that is to do row 2 minus 2 row 1. Okay, if we do row 2 minus 2 row 1 and we replace the contents of row 2 with that, you'll just get 1, 2, 3 across the top. You get 0, 0, 0 across the bottom. Okay, now if we put that back into equations, because remember that came out of equations, it's an augmented matrix, we're going to obtain x1 plus 2x2 is equal to 3. Okay, now that means that whole system reduced down to that one equation. Now generally what we'll do then is solve for the variable that's on the left. As you see, x1 plus 2x2 equals to 3 is the same thing as saying x1 is equal to 3 minus 2x2. Okay, now if you have something of that form, you're probably used to seeing things like y equals something x, like mx plus b, for example. In that case, y was the dependent variable, x would be the independent. Now here I have x1 is equal to 3 minus 2x2. What that means is that x1 is dependent, x2 is independent. That's called the general solution to the system. Okay, now there's nothing magical really about solving for x1 versus x2. I could have just as easily solved for x2 and then had x2 being the dependent and x1 being the independent. But it's a convention in mathematics to solve for the leftmost variable. Okay, so that's why I chose to solve for x1 and say x1 was equal to 3 minus 2x2. That would make x2 the independent one. Okay, so that's pretty much how we're going to do all these problems. Mostly you'll be asked how many independent variables do you have. Okay, so whether you'd solve for x1 or x2 in this particular situation, wouldn't have made that much difference if you were answering that question. Okay, a shortcut for saying x2 is independent, because we don't want to write out every time x2 is independent, we just say x2 is equal to x2. That means it can be anything. Okay, so that's just a shortcut way of saying independent. That's going to make our general solution look like x1 is equal to 3 minus 2x2, and then you say x2 is equal to x2. It's just a short way of saying x2 is independent. You'll see that a lot more in upcoming sections than you do really in this one. Okay, to find a particular solution, we just saw the general solution. To find a particular solution to a system, assign a value for the independent variable. What we're going to do is basically find a point. Okay, for example, if we were to assign x2 to be 1, then since x1 was 3 minus 2x2, x1 is going to be 3 minus 2 times 1, which is 1. So that point would be 1, 1. That's a particular solution. Okay, if instead we were to say x2 is 2, then x1 would equal 3 minus 2 times 2, which is negative 1. So that point would be negative 1, 2. Okay, so there's a couple of particular solutions, a couple of points that satisfy the system. Okay, that's the difference between a particular solution versus a general solution. General solution gives you the setup of all of the solutions. Particular solution is just a specific point that fulfills the conditions. Okay, next we need to know the dimension of a solution set. This is basically a definition. The dimension of a solution set is the number of independent variables. Okay, so if you're asked for the dimension of a solution set, it's just the number of independent variables. You just need to count them. In the previous example, since we just had one independent variable, we had a one-dimensional solution set. Okay, next example. What's the dimension of the solution set for this matrix? The first row is 1, 0, 1, 3. Second row is 0, 1, 2, 0. And the last row is all zeros. Okay, well, I need to keep in mind it came from a bunch of equations, right? So put it back into equations. I would get, for my general solution, x1 plus x3 is equal to 3. x2 plus 2x3 is equal to 0. Now we said we were going to solve for the one on the left, right? So x1, I want to solve for that. x1 is equal to 3 minus x3. And then x2 is on the left in the second equation, so x2 is equal to negative 2x3. Okay. Remember to account for every variable. I put that there because I'll see people often write down, okay, well, x1 is this, x2 is that, and they'll go on their merry way, and they'll miss the whole fact that there were infinitely many solutions there. We had x1, it was 3 minus x3. We had x2, which was negative 2x3. But what about x3? x3 is going to be independent. Okay, so x1 is dependent, x2 is dependent. They're both dependent upon x3. But x3 is independent. So rather than writing out x3 is independent, you can just write x3 is equal to x3 and say the same thing. Okay, so this system has a one-dimensional solution set. Okay, how do we know if a system has infinitely many solutions? We said that's what this section is all about. Well, if a consistent system has one or more independent variables, that's the magical way of telling, it has infinitely many solutions. The reason is because an independent variable can be equal to any value in the world, any real number. And since there are an infinite number of real numbers, there are infinitely many solutions. Okay, for example, find the general solution for the system represented by this augmented matrix. First row is 1, 2, 3, 0. Second row is negative 1, 1, 3, negative 6. Third row is 3, 4, 5, 4. Okay, I just want to start Gauss-Jordan elimination on this. So I would first need to take care of the negative 1 that's in the second row. As you see, I already have a positive 1 in the upper left-hand corner, so I don't have to worry about trying to get that. But I do need to get rid of that negative 1. I need for that to be a 0. I also need for that 3 to be a 0. So I'm going to go ahead and take care of those in the same matrix. I need to do row 2 plus row 1, and then row 3 minus 3 row 1. So remember, since I'm in column 1, I want to use row 1. Okay, that gives me the first column looking like I want it to. Okay, so I have that 1, 0, 0. Remember what I'm going for is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so first column looks good. Then I move to the 2, 2 position. In the 2, 2 position, I have a 3. I need for that 3 to be a 1. The best way to do that without messing up the 0 in front of it is to do its reciprocal, which is 1/3, times it. So 1/3 of row 2. As you can see, that's going to make the 3 a 1. It's also going to change the 6 and the negative 6 to be a 2 and a negative 2. Okay, now I want to take care of the 2 that's above that 1 and the negative 2 that's below that 1. I want both of those to be zeros. So if we'll do row 1 minus 2 row 2, then row 3 plus 2 row 2. That makes the second column look like I want it to look. Okay, so first column looks good, second column looks good. What about that third column? Is there any way I can ever make that third column 0, 0, 1? No, there's no way to change that 0 that's in the 3, 3 position. There's no way to change that 0 into a 1 without messing up the zeros before it. So at this point, I'm finished. That is as close as I can get to what I was going for, which was the 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so at this point, I'm ready to write out my general solution. Remember, it's an augmented matrix. So I can say x1 minus x3 is equal to 4, and then x2 plus 2x3 is equal to negative 2. Solving again for the one on the left, you're going to get x1 is equal to 4 plus x3, and then x2 is equal to negative 2 minus 2x3. All right, what about x3? x3 is just going to be x3. You probably guessed that one. Okay, so that's going to be my independent variable. So that system has infinitely many solutions, and it's a one-dimensional solution set because there's one independent variable. Okay, now I don't want you to think that all systems just have one independent variable, so I have a few for you to look at that have more than one, or in some other sections we'll look at some that have none at all, of course. For the following augmented matrix, what is the dimension of the solution set? Okay, as you see, I have 2, 4, negative 6, 10 across the first row. Second row is 1, 2, negative 3, 5. Third row is negative 1, negative 2, 3, negative 5. Maybe you're already seeing some similarities between those rows. Maybe not. Anyway, what I need you to try to do is to get a 1 in the upper left-hand corner where that 2 is. Now you could do that a couple different ways. You could divide by 2, which would be like multiplying by half, or you could switch row 1 and row 2. I generally prefer to switch rows because there's less arithmetic involved. So I would switch row 1 and row 2 and then have the first row being 1, 2, negative 3, 5. The second row being 2, 4, negative 6, 10. Okay, that gives me a 1 in the upper left-hand corner. Then we want to get zeros below it. So I want the negative 1, I want the 2 to be zeros. Okay, I can accomplish that by saying row 2 minus 2 row 1, and then row 3 plus row 1. Remember, if I'm in column 1, I want to use row 1. Okay, and remember, whatever you write first, like if I write row 2 minus 2 row 1, row 2 is the one that's going to change. Okay, in this case, look what happens. I get 2 rows of zeros at the bottom. So basically my last 2 equations completely canceled out. This whole system reduces down essentially to one equation. This is one of those systems where we have intersecting planes. They're all coinciding planes. Okay, so I get x1 plus 2x2 minus 3x3 is equal to 5. Solving for the guy on the left again, I get x1 is equal to 5 minus 2x2 plus 3x3. That means that both x2 and x3 are independent. So that system has a two-dimensional solution set. And like we said, because it all reduced down to one equation in a 3x3 system, it was like 3 coinciding planes. Okay, a two-dimensional solution set. All right, what's the dimension of the solution set for this augmented matrix? That one's looking pretty empty, isn't it? We have 1, 0, 0, 5 in the first row, and everybody else is a 0. Well, let's write out the solution. If we put it back into equations, we get that x1 was 5. We didn't have any information about x2 and x3, did we? Well, since the coefficients of x2 and x3 are all zeros, the values of x2 and x3 could be anything. Okay, in other words, they're both going to be independent. We just had x1 was 5. What about x2 and x3? Well, they're not there, so we say that they're independent. They could be anything. Obviously, if I multiply any number by 0, I'm going to get 0. So anything for x2 and x3. So that has a two-dimensional solution set. All right, does a row of zeros mean there's going to be infinitely many solutions? A lot of people seem to think this. In a lot of the examples, in fact, all of the examples, I guess, that we did, we had a row of zeros. Does that mean there's got to be infinitely many? No. Try not to make that a rule, okay? A lot of people try to follow that and then they get messed up. Look at this system. I have 1, 0, negative 2, and then I have 0, 1, 5, and then I have a row of zeros. So some people would jump to the conclusion, oh yeah, that's infinitely many solutions. But if we write out the solution for this, this gives me x1 is equal to negative 2. x2 is equal to 5. There is no x3. So what's that mean? That means there's only one solution to this. It's a unique solution. Okay? There's only one solution. There were not infinitely many solutions. Every variable is equal to a number. Therefore, there's only one solution. I hope that helps clear up the myth about the row of zeros. Okay, the only way we'll ever get infinitely many solutions if there's one or more independent variables. That's the only real way to tell. So when you write out your general solution, if you have an independent variable, then there's infinitely many solutions. If there's not an independent variable, then there's not infinitely many solutions. Okay, try not to make any other rules than that. Okay. All right, that was section 1.3. Consistent systems with infinitely many solutions. The important thing to remember here is that if you have an independent variable or more than one independent variable, you have infinitely many solutions. Okay, so give this one a little bit of practice and get used to writing out like x2 is equal to x2 if that means x2 is independent. And we'll use that a lot more in future sections.